Welcome everyone. On our previous class, we have seen the RL and RC circuits, RL and RC series circuits. Now, in this class, we'll be talking about if we combine this RL and C together in a single circuit in series combination. Now, here is the circuit that we can see. The conditions are quite similar, and if we apply KVL to this circuit, we will get V equals VR plus VL plus VC, which is the voltage drop across the resistance, the inductance, and the capacitance respectively. Now, the voltage can be written as IR for the resistance, I into j omega L for the inductance, and I into 1 over j omega C um, for the capacitive element. Now, let's look into this graph over here. It is quite similar to the previous one, but um, here we can see there are two elements. One is VL and another one is VC, right? So the values of VL and VC, actually this is a circuit which is this is the phasor diagram for a circuit which is in resonance. We'll talk about resonance later, but this in real life condition can happen, but mostly there are two conditions um, which may occur in this circuit. The first condition is mm, when the XL value or the value of the inductance is greater than that of the value of the capacitance. Now, if we look into the magnitudes of this XL and XC, we can see for the first case, for the first case, we see the value of VC has become shorter, or the phasor has become shorter than that of the value of VL. That means VL is also greater than VC over here. Now, if this thing happens, we can easily say we have done the vector summation. If the magnitude of a vector in a particular direction is more than the magnitude of the vector in opposite direction, the resultant vector can be written as, if this is VC and if this is VL, the resultant vector will be VL, which is greater one, which is the larger one, minus VC, right? So here what I have done is I have taken a vector which is the resultant vector, which is VL minus VC here, and placed it over here, right? So that we can find the resultant voltage from this condition. So this is the condition where the inductive element actually overrides or overcompensates the capacitive element, right? For the second case, where XC is greater than XL, that means the capacitive elements is much more than that of the inductive element. We can see that the capacitive value, the vector for the capacitive element is much greater than that of the inductive element. So in this case also, the resultant vector will be here. In that case, it will be XC minus XL, right? Or in case VC minus VL, right? Whichever vector you take. So here also we get the value VC minus VL, right? So here we can find the voltage, the resultant voltage that is being applied to the circuit. So these are the two conditions, these are two possible conditions that can happen in case of a series RLC circuit. Now these are the diagrams. We are quite familiar with this diagram. as we have seen in the previous two, RC and RL, they are basically the same. This is the diagram for a purely sorry, it is the diagram for an RL circuit where with resistance only inductive element is applied, as because uh, as XL is greater than XC, only inductive element or inductive properties will be shown by the circuit, and here we will find the RC properties, right? The RC properties can be seen in this um, diagram. Now, um, the condition for resonance is whenever these two vectors are equal in magnitude. If these two vectors are equal in magnitude and opposite in direction, let's say this is VL and this is VC, these are equal in magnitude and opposite in direction, then VL minus VC or VC minus VL, whatever you take, will be equals to 0. Then the circuit will act as a purely resistive circuit, right? So whenever there is a placement of inductive and capacitive element in the circuit in series, although the circuit behaves like an resistive element with a variable frequency, then we can say that the circuit is in resonance, right? Now, to find the impedance of the circuit, just we have done what we have done in the previous classes, that V equals to I multiplied by R plus j omega L, R plus j omega L and j omega C, and we have taken j common, and this is the value of impedance that we have got over here, right? Now, if the circuit is in resonance, then uh, it will be only purely resistive circuit, right? It will be only purely resistive circuit. So this portion will not be there for a purely for a circuit which is in resonance. So to make that happen, we have to take a condition where this element becomes zero. This element becomes zero. So if this element becomes zero, then the impedance will be equal to the resistance only, and the circuit will behave like a purely resistive circuit. Now omega L will be equals to 1 by omega C. So this is the condition for resonance, right? So from here we can write omega square equals 1 by LC, and or omega is equals to 1 by root over LC. This is the condition for resonance in a resistive in a RLC circuit. Now this condition is applicable for both series circuit as well as parallel circuit. We will talk about parallel circuits later. And in terms of frequency, we can write it as 1 by 2 pi multiplied by root over of LC, right? So these are the frequency condition and the angular speed condition for um, the circuit having resistance, inductance, and capacitance in series to be in resonance, right? So next we will see that how parallel circuits react to this, right? So these are the inductive, capacitive, and resistive element having a voltage source V, having a variable frequency, providing a current I. These are R, L, and C. The current over here is IR, this is IL, and this is IC. Now, the inductive element can be written as XL and the capacitive element can be written as XC, right? So the conditions over here are quite similar, but in the mm, parallel circuits, there is no change in voltage. So we'll the take KCL over here. We'll apply KCL over here. On the previous ones, we have been applying the KVL, but here we will use KCL because applying KVL is no use in this circuit because these are all placed in parallel. Uh, IR plus IC plus IL, sorry, IL plus IC, right? Now here, IR can be written as V by R, IL can be written as V by XL, and IC can be written as V by XC, right? So here also, if we take V common, we'll get 1 by R plus 1 by XL plus 1 by XC. Now XL and XC we have seen already can be written as j omega L, and XC can be written as 1 by j omega C, right? We'll replace that 1 by R plus 1 by j omega L, and this will become j omega C, right? Now from our previous calculations we have already seen that V equals 1 by R plus mm, j multiplied by omega C minus of 1 by omega L, right? Now here the condition becomes so actually what is this? In the previous one we have seen that Z equals to R plus j multiplied by omega L minus 1 by omega C. Now here this is actually the inverse of that. So for resistive element we will get a value of Z as 1 by R plus j of omega C plus 1 by, sorry, negative omega L, right? So now here also we can see that if the circuit uh, is in resonance, then the only condition is that this value must be equals to 0. So omega C minus of 1 by omega L will be equals to 0 for resonance, right? For resonance. So omega C will be equals to 1 by omega L. Now omega square can be written as 1 by LC, or omega is written as LC. So this is again the condition for resonance. For frequency the value will be same, 1 by 2 pi multiplied by root over of LC. So this is the frequency condition. So these are the conditions for um, a circuit to be in resonance having series and parallel inductive and capacitive elements, right? So here I want to show you one thing, that um, that if this is the graph where omega is over here and these are the resistive values, then the graph will show like this or will be like this. Now this is the value of the resistive element in the circuit, or omega R, right? This is not actually omega R. This can be written as R, as we have taken omega along x-axis we will write it as omega R, right? So this is the value where uh, this is maximum, or the resistance is maximum. So the current is minimum, right? So these are the values. So these are the values. So prior to that, we can see that XL, this XL is greater than XC, right? So it will behave as RL circuit, right? And similarly, we have also seen that here the condition is XL greater than XC greater than XL. So the circuit will behave like an RC circuit. So here in the graph, we can see that if the values of um, the frequency is lower, then the circuit will act as an RL circuit, right? Or inductive circuit. So the value of the frequency, these are lower frequencies, omega L, right? And this is omega C. So here the circuit will act as RC circuit, right? So it is actually uh, a band pass filter, which will allow, sorry, it is a band stop filter. It is a band stop filter which will allow only a certain frequency to pass through the circuit and blocks every other portion or every other frequency. So it is a band stop filter. Now, in case of current, or in case of the parallel circuit, what happens is mm, we can see about the current, not parallel circuit. We can see the graph of the current. Now, for the current at RC, or sorry, at R, the value of current is minimum, as we have seen, right? And for XL, it goes to the maximum, and for XC also it goes to the maximum. So it is acting like a band pass filter. So series and parallel RLC circuit can also act as a filters. They can act as filters, right? So the quality factor can be achieved. We don't have quality factors in our syllabus, so no need to do that. Uh, we just have to know the resonating conditions or resonance condition for these two circuits. Uh, Here we can see the resonating condition for the impedance will be XL equals to XC, right? We have seen the magnitude of these two are same. So whenever the XL value is equals to XC, then only resonance can happen. Otherwise, it cannot. And here also we can see that when Z equals to R only, then resonating can happen in this parallel circuit. So that's it for today. We'll talk about AC circuits uh, in our next class, right? Thank you. Stay safe.